So there are a couple of reaction mechanisms that the IB curriculum holds you responsible for understanding. We've already gone through a couple of these. One would be electrophilic addition reactions to alkenes. Another would be the SN1 and SN2 reactions. But one of the other reactions that they want you to be familiar with is what's considered the nitration of benzene. All right. So the reason that this reaction is fairly important is that benzene is a readily available organic chemical. But the thing about it is that as long as it's pure benzene, it's not that useful synthetically. All right, there's not a whole lot of reactions you can do with just plain old benzene. All right, but if you're to put a nitro group on this, and when I say nitro, I mean NO2, and we'll show the structure of that in just a little bit. It opens up the ability to further functionalize this the molecule a lot more, all right, than if you had just plain old benzene. All right, sometimes in organic chemistry, people just refer to that casually as saying it puts a handle on the molecule. All right, consider like having just a really smooth ball. All right, you don't have anything to, like a really smooth bowling ball, you don't really have anything to hold on to. But once you put a handle, if you were to be able to install a handle, you'd be able to do something. You'd be able to grab onto it and manipulate it. All right. So that's kind of a metaphor for what we're talking about here. We're putting a group on that then allows you to do further functionalization. And when I say functionalization, I mean being able to perform chemical reactions. All right. So an analogy to this concept that we're making it more useful would be the reaction that we did before, where we did the radical halogenation of alkanes. All right, remember, alkanes by themselves are not that useful as synthetic starting materials. All right, there's not a whole lot of reactions that you can do with them. Yes, you can burn them, but in terms of what chemicals would react with an alkane, there aren't a whole lot. The one reaction that does work is the radical halogenation, which is where you put like a bromine or something on the molecule, and once you get that a halogen on the alkane, then you can do a lot of stuff with it. All right, so that's just kind of an analogous rationale for why we're doing this. All right, so in this reaction, what it makes use of is it's an anhydrous mixture of two chemicals. All right, we'll actually have three chemicals in the reaction mixture. We're going to have benzene, we're going to have nitric acid, and we're going to have sulfuric acid. All right, and notice I say anhydrous. All right, and what that means is no water. All right, and while in just about every single science experiment you've ever done that involved mixing chemicals, we almost always have used water. All right, when you're doing synthetic organic chemistry, you have to remember sometimes water does some things that we don't want. All right, and this is a case where water would actually be bad to have around in the reaction, and we'll show why in just a second. All right, so I drew the structure of nitric acid here, and if you had the structure, if you were to draw a regular Lewis structure showing all the electrons, it would look something like this. All right, we would have two lone pairs on this oxygen, we'd have a double bond between here, we'd have a single bond here, three lone pairs there. And one thing that you notice about the structure is if you're paying attention to formal charges, that puts a negative charge on this oxygen and a positive charge on this nitrogen. All right, but the overall charge on the entire molecule would be neutral. All right, so the one and that's why when you draw the formula for this, a lot of times it's just shown as HNO3. All right, you don't show the charges because overall the charge is neutral. All right, so one thing about this structure is you can draw a resonance structure with this. All right, which would go something like this. Draw an arrow from one of these electron pairs here going down to the nitrogen, show this electron pair from the double bond going up to the oxygen, and what that would give you is this particular form right here. All right, and so remember, one of the purposes of showing resonance forms is that it allows you to get a sense of whether electrons are individually owned by atoms or whether they are more or less shared between atoms. All right, so the fact that we can show these two resonance forms of nitric acid indicates that it's not really true to say that this oxygen right here has a total -1 charge. Nor is it true to say that the other oxygen right here has a complete -1 charge. There's a way that you can show this where you show that the electrons just being shared between all of the atoms, all right? And so that's why a lot of times if you were to draw something like this, you might also just show it like this. So NO2 with a bond to it is essentially the same thing as this right here. All right, and remember, what this does is it captures that it's got the correct number of atoms, it's got the correct overall charge, but it doesn't try to make a point of showing exactly where those formal charges are. All right, so and here is the Lewis structure of sulfuric acid. One thing I just want to point out about sulfuric acid is notice that sulfur, this is the particular form of this Lewis structure shows it where the sulfur is exceeding the octet rule. All right, if you count the total number of electrons that sulfur would have, it's got 2, 4, 6, 8, 10, 12. All right, and remember, sulfur is one of those atoms that can exceed its octet, and it does that because it's one of those third row or third period elements, and it's got available d orbitals that it can use to make those bonds. All right, and I actually talked about this in an earlier video, and I'll put a link to that video where it talks about like how some molecules can do that. All right, so one thing about nitric acid and sulfuric acid is, if you recall from the acids and bases unit, they're both considered strong acids. All right, which means if you put either of these into water, each of them would completely give away their acidic hydrogens to water. All right, so if you put nitric acid in water, all of the nitric acids are going to give their H+ to water. Same thing with sulfuric acid. All right, so that's why they're both considered strong acids. All right, but just because they're both very strong acids and completely ionize or give their hydrogens to water, that doesn't mean that they're equally strong acids. All right, and so it's kind of like saying if you had two heavyweight boxers. All right, well, any of these boxers could beat your average person. All right, but that doesn't mean that they're completely equal if you compared them to each other. All right, if they were to box each other, one would most likely be stronger than the other. All right, so between these two acids, all right, nitric acid is going to be a weaker strong acid, and sulfuric acid is going to be stronger. All right, and the reason that what that means is that if you mix these two things together, remember they're both acids. Both of them have a potential to give an H+ to its neighbor. All right, so if you mix them just with each other and there's no water around, would nitric acid be likely to give its H+ to sulfuric acid, or would sulfuric acid be likely to give its H+ to nitric acid? All right, and what this means is that sulfuric acid would be much more likely to give its H+ to nitric acid. All right, so what happens in the mechanism of this reaction? All right, so first I'm going to just show these two structures side by side. All right, and remember that we said that sulfuric acid is a stronger strong acid. All right, so if it's a stronger strong acid, think of the sulfuric acid acting as an acid, wanting to donate its H+, and think about nitric acid acting as a base, which might sound a little bit weird that a strong acid might act as a base. And the only way that can happen is if you treat it with a really, really, really stronger acid. All right, so the mechanism that we can show is an electron pair from this oxygen right here is going to attack that H+. These electrons go onto the oxygen. All right, and what that ends up creating is this structure right here. All right, so you'll notice down here, before we had two lone pairs, now we've just got one. That puts a formal charge on that oxygen right there. And for the H2 SO4, notice I'm just going to write it like this. All right, I could draw this out as a structure, and if I did that, first of all, you can pause the video here. Try to draw that structure of what you think will get created here based on the results of this arrow pushing. All right. Well, I can abbreviate it like this, and if you want to know what that structure is, get rid of this hydrogen right here and draw three lone pairs on that oxygen and then put a negative charge on that oxygen. That's what the structure for this formula would correspond to. All right, so the next thing that we can do as far as arrow pushing is, and this is going to be something that's that's very common in reaction mechanisms. Take a look at this part right here. All right, when you see this, it should, if you see this enough times, you get used to this common occurrence. This thing is set up for water to leave. All right, and so what I mean by that is, what's the difference between, what do we need to basically kick out a water molecule? All right, well, water has a neutral oxygen and it's got a second electron pair. All right, well, therefore all that we need is that for these two electrons in this bond to go on to this oxygen, and then that just makes a water molecule. All right, that provides the second of the electron pairs that it needs, and it gets rid of that positive charge. All right, so what we're going to do is we're going to do this. An electron pair from here goes in there, and the water leaves, and that ends up making this. All right, that ends up making this species right here, and that's called a nitronium ion. All right, which is sometimes shown as NO2+. All right, and the other thing it makes is water, so I show that just as a product here. One thing I just want to point out is the way this is drawn. It's a good review of Vesper. Remember, the geometry around this nitrogen would be expected to be trigonal planar, but once you do this right here and you've got the NO2, notice I drew it in a straight line. All right, because that would be linear. That would be linear triatomic. All right, so that's why I don't show it like a boomerang. I show it like a straight line. All right, so one thing about this is it only exists in what's considered in situ. Right, this is an unstable material that it's only going to be able to exist in that pure sulfuric acid solution. All right, in fact, if you treated this, if you had a lot of water around, this would not exist. All right, so you have to make it as you use it. All right, so the reaction that's going to occur, we take again, we have benzene that's in solution, and once that nitronium ion gets created, it can then act as an electrophile compared to benzene. All right, so what benzene is going to do, it's going to attack that nitronium ion with its pi electrons. And remember, we've got three pairs of pi electrons that are being shared among all those atoms, and two of those pi electrons attack that nitrogen. That creates this intermediate right here. So we're going to make a bond between this carbon and that nitrogen. That then puts a positive charge on this neighboring carbon. All right, and then remember we've got this H2SO4 HSO4 minus that got created before. That can act as a base to abstract that hydrogen. These electrons go back in, and then you get your nitrobenzene. All right. So one thing that I want to point out about this, we used a molecule of sulfuric acid here, but we ended up regenerating a molecule of H2SO4 here. All right. So if you use one and then you make one, there's no net consumption, there's no net production. All right, therefore, H2SO4 is a catalyst in this reaction. It doesn't get consumed. So if you wanted to draw a reaction for this, you could do it like this. All right, so what actually gets used? We use up a molecule of nitric acid. We use a molecule of benzene, and what ends up getting created? We end up making a molecule of nitrobenzene right here, and the other thing that gets created is water. All right, so that's the way that you could show the reaction. I do want to point out that the IB curriculum has a way of showing this a little differently. All right, so instead of showing it with the 3 distinct double bonds, sometimes they show that with the circle in the middle. And another way that you can show the mechanism is, okay, and if we abbreviate the nitronium ion like this, you show the electrons going like that. All right, and they do this thing where they draw this semicircle in there with a positive charge in the middle. All right, again, that's in that essentially represents this structure right here. All right, one thing I don't like about the way they do this is that if you take a look, the positive charge would actually be on one of the neighboring carbons. All right, whereas you have no sense of that when you draw it this way. But anyways, you would end up getting this, and you'd also make H2SO4 as a product. So write in H2SO4 right here.